user delays, and so this is something that should be considered, especially in urban areas where you're going to have a high impact on a lot of road users. This was a study done out of California, and this was just a kind of a study to kind of verify that although people don't generally want to be inconvenienced by accelerated construction processes, after they actually do the rapid rehab, they generally have a favorable impression about what had happened. Just a couple quick examples, by no means exhaustive, of some of this thought process. The Tollway was thinking about, the Illinois Tollway near Chicago was thinking about reconstructing some of their major principal arterials that they own, and jointed plain concrete was selected as one of the options that they looked at. And they wanted to do 100% recycling of the existing pavement, and they began a study to look at, okay, where we could recycle what materials could we recycle into the new pavement, in what layers, and also using higher amounts of cement replacement with other pozzolanic materials such as slag and flash. And in this example, they're using up to 35% replacement of cement. They also used, in this two-lift scenario, some of the coarse wrap or frap particles, which is just fractionated wrap, in the bottom lift. And despite having what was measured as lower flexural strengths with the wrap material, it was placed in the bottom lift, and some testing showed that it wouldn't impact the fatigue life to have this slightly lower flexural strengths that still meet their existing specifications in the bottom lift. So they're able to use existing roadway right back into the new roadway with the two-lift system. They actually expanded. That was kind of a test case, and the following years they reconstructed about 60 centerline miles of I-90. And this shows the existing pavement structure that was out there. They had an asphalt overlay of a 10-inch jointed plane, 12-inch granular subbase, and over 300,000 ADT with 11% trucks. This pavement structure roadway was going to be expanded from 2 lanes to 3 lanes at one location, and 3 lanes to 4 lanes at another location. That's in one direction. So there was a lot of variables going to change, and so there had to be a lot of planning if they were going to use all the material in the existing structure in the new pavement, and also deciding which layers to use within the jointed plane system that they were going to use. And the agency really wanted to recycle everything, and this is the final pavement structure generally they used throughout the reconstruction process. A two-lift system with a bottom lift with recycled asphalt wrap in it, in the coarse aggregate fraction, a virgin concrete, the top lift, so we didn't necessarily use a premium surface, but just a regular dolomitic coarse aggregate on the surface, and that was supported by a stabilized base with warm mix asphalt that actually used the wrap, the fine wrap that was taken, and some of the coarse wrap from the existing roadway. The crushed concrete subbase came from the existing concrete slab, and the granular subbase underneath that was, again, from the original pavement structure. So this project also had staging areas that the contractor could use along the project to minimize the hauling distance for setting up his processing plants. So as you can see, many different use of innovative design, recycled materials, co-product materials involved. And there was actually recycled shingles used in the warm mix asphalt as that I failed to mention. Use phase considerations. Use phase considerations really depends on the type of pavement, but in general, for instance, if we were using principal arterials, we're going to have a big impact on fuel consumption. The smoother the road is, and also the longer the pavement has with little to no distress, we're going to have a a better life cycle assessment. As you move to lower and lower volume roads, the use phase considerations are not as high of an impact as the material and construction phase that dominate the environmental impact when you run an assessment. Other use phase factors that one may consider would be noise, skid or friction, the amount of roadside pollution or particulate matter, likewise stormwater, if that's an objective to have some kind of minimum quality of stormwater that's discharged into local waterways that may need to be handled in the use phase. Also, as I mentioned, the urban heat island effect is a use phase factor, along with other factors I've listed here: aesthetics, utility cuts, manholes, and their effect on the use phase. So, in summary, there's a lot of integration of various factors when selecting the pavement types to analyze for the design, and that includes the materials that were talked about in the beginning, the layers, and then we're going to have some more conversations about the construction and traffic management plan that are important in selecting the design that's going to be a more sustainable design for the agency. Likewise, recycled or locally available materials are going to have the lowest impact, assuming they can meet the design objectives. Future directions or technologies, clearly having a mechanistic-based design will help analyze different types of pavements or different design lives that you want to compare when you're trying to make a sustainable pavement design more sustainable. Performance-related specs can help by not tying down contractors to a method that they have to use. They may find another process that can save money. New materials, we'll see those more often to meet objectives for sustainability, like maybe potentially photocatalytic cements or albedo requirements, and really the idea of now being able to integrate cost and environmental impact as in the criteria, and that the environmental impact could be a global warming potential number or a change from previous designs, or it could be a rating system type approach. There are many ways to do that. Finally, there's still needs to look at more in-depth preservations and recycling in future designs. I think that's it, Kurt.
All right, thank you, Jeff. We appreciate that. And once again, I would like to remind all of the attendees that you're welcome to submit questions at any time using the chat box feature on your control screen, and then we'll try to get through those at the end of the session. So we've talked about concrete materials, concrete pavement design. We now want to move and talk about concrete construction, and we'll have Mark Snyder provide us some information on that. Mark?
How are you doing, Prashant? Can you hear me okay here?
Yes, you should be good to go, Mark.
Okay, very good, thank you. And I am going to talk a little bit about construction considerations, factors that impact sustainability that you can control during the construction process, as well as basic strategies for improving the sustainability of, actually two parts here. The first part is going to be about pavement construction in general, and then the second part deals more with things that are specific to concrete pavements. So the key construction issues that impact sustainability, and again, this is just for construction in general, again, the first half of the presentation being about general construction issues. We can kind of break most of these things down into four major categories. As you see listed there in black: energy consumption, impacts on the surrounding areas, and that includes both the particulate emissions and exhaust emissions at the local level, as well as their impact globally, and impact on wetlands and streams, as well as the things that we think of in terms of the impact on the traveling public, traffic delays, and local impacts like congestion and noise. And then the third category, impact of construction quality on pavement performance and overall service life, including both the impacts of surface texture on the functionality of the pavement, the safety, the friction characteristics, and the noise characteristics, tire-pavement interaction, and roughness, as it impacts not only the ride quality of the traveling public, but also the impact that it has on use phase fuel consumption, and ultimately even on maintenance and on operations costs for the vehicles. The fourth major category being economics of construction practices. All the things that we may do and consider to improve the sustainability of a pavement construction process. These things may and often do have a cost associated with them, and often we're willing to bear those costs, but we need to consider what they are and evaluate them in the context of the larger picture. And those are not only the construction-related costs, but also the impacts that certain practices may have on the use phase. So those are the four major categories, and I'll be talking about each one of those in a little bit more detail in the following slides. First one is the most obvious, energy consumption. I think that's probably the first thing we think about, or most people think about when we think about construction activities. You look at all that heavy equipment moving up and down the job site. Construction is inherently a very intensive, energy-intensive process. There's a lot of activities involved in all phases of the operations, the excavation work, moving of earth from one end of the job to another job, and the processing of materials and the placement of those materials, and the efforts that are required for compacting foundation layers and consolidating concrete layers, and then the energy even in the relatively minor operations of texturing a concrete pavement, for example, and cutting joints. In the grand scheme of things, perhaps relatively small, but they all add up. And as I've mentioned already, there's a lot of equipment that's involved. Excavators, hauling equipment, crushers, so on and so forth, all the things you see listed here. They've all got an energy cost associated with them. And the energy really, we see the operational efficiencies that are involved with all these pieces of equipment. We see them operating and consuming fuel, but even there's some variability in the amount of fuel that's consumed just depending upon the way that the equipment is operated. The amount of time that it is spent idling, matching proper equipment sizes. If you got oversized equipment on a relatively small job, you are probably using more energy in the operation of that equipment than would be used if a more appropriately sized piece of equipment was used on that job. Idling time, things like that, matching of the equipment capacities and so forth. And there are also the external factors, things that are independent of the equipment that are used but are more related to the site operations and the site conditions. These things have to do with the staging that's used, the distance from the storage and stockpile areas to the places where the materials are being used on the job, even things like the quality and condition of the haul roads. Much like we would see on, it's fairly obvious that if you have a relatively soft haul road, the equipment is essentially always driving uphill as the wheels are sinking down slightly into that road, as opposed to having the higher costs perhaps of building a more stabilized haul road, but then perhaps the lower operational costs that are associated with that. So lots of different factors. Even something as simple as energy consumption becomes relatively complicated when you look at all the different factors that impact the energy consumption on a particular job. One way of looking at the back end of the energy consumption, of course, is the emissions that are produced, the particulate matter and the greenhouse gases and so forth. The EPA has come up with this concept of emissions intensity, which is often measured in terms of millions of tons of CO2 equivalents per thousands of dollars. And in 2009, they put out this publication which cited 2002 figures looking at many different sectors of the economy and the total emissions that are being produced, which you see in the green bars on the chart, and then the emissions intensity, which is showing basically the emissions per thousands of dollars of product and economic benefit. And really, when you look at this, first thing you see is, well, certainly construction is up here in the top three of the biggies in terms of total emissions. But again, when you look at the essential nature of construction to our infrastructure and the economic benefit that is derived from construction, the emissions intensity is actually relatively low compared to oil and gas, chemicals, iron and steel, production of cement, production of lime, very intensive types of processes. Within the construction process, we can even further break it down into the highway and road and bridge component of that, and you can see that is about double what the overall average of construction is, but still even at 0.49 million tons per $1,000, it's still in pretty good company among the lower emission intensities of the sectors that are cited here. So we need to be cognizant of that, but I don't think we are quite as bad in terms of an energy intensity standpoint as we often are portrayed as being, perhaps. Another impact is on the effects of traffic delays, and there are numbers of impacts that traffic delay has on sustainability, and go right back to the energy and emissions aspect again. Energy and emissions contribution of traffic delays a lot of times are ignored in life cycle assessments. We pay attention to the consumption of the fuels in the construction, but not to the aspects of the traffic delays. There are some tools available that will help us to quantify both the emissions of the equipment that we just looked at, as well as the emissions due to traffic delays. The latter is the EPA's MOVES software, MOVES software, will calculate emissions and energy consumption associated with changing of driving schedules and traffic delays. This slide kind of summarizes the MOVES software, which I just mentioned, and also the EPA's non-road software, which will look at the impacts of the non-road equipment on both energy consumption and atmospheric emissions. There are other tools available as well, and those are cited down here at the bottom, but we won't go into details on them. But there are tools available for calculating and assessing these types of things. We'll take a quick look at, and again, not looking really how to use the MOVES software as much as to look at what it does. And this particular scenario, this particular case study is looking at a 7.6 mile long work zone that was analyzed, and 3 different traffic scenarios were analyzed in terms of the staging. As you see there, partitioning the project into 4 different work zones and using nighttime closures. Alternative number 1. Alternative 2 was to partition it into simply 2 work zones and using a little longer closures, 16-hour closures. And then the third option was to use no partitioning whatsoever, just do it all in one big long closure, 32 hours long. And the MOVES software was then used to assess the impact on global warming potential as a percentage of total global warming potential for the project, including materials and construction phases. And you can see there's a bit of a difference there between the two, between the different scenarios. It was 1.3% of the total in the best case scenario, which was to break it down into the 4 smaller work zones and using nighttime closures to minimize the traffic delays, to the no partitioning and the longer closure having the basically double the impact due to the emissions due to the delays. So these tools are available and offer another way of looking at the impacts of construction. There are also impacts of construction on the surrounding areas. These include emissions from the equipment exhaust, obviously, airborne particulates. That's not only exhaust types, but it's the dust and debris and so forth from construction operations. There's the noise that's generated from the construction operations, the impacts that construction has on local businesses and residences and local traffic, lack of access to the residents and lack of access of customers to businesses and so forth. And there's an economic and societal cost to these types of things. There's also, of course, the construction in wetlands and streams and environmentally sensitive areas, potential for impact from those things as well. So we'll talk about how to mitigate those things a little later on. We've mentioned how to quantify the greenhouse gas emissions and so forth from traffic delays and congestion. We need to recognize that construction zones are a major source of congestion. US DOT in 2006 provided an estimate that said that highway construction zones account for about 24% of non-recurring congestion. And by non-recurring, we're talking about for example, recurring congestion would be things due to like lane drops where you're going from 3 lanes to 2 and there's always a backup at this